Guys, welcome back to Logarithmic Equations. We're doing explanations here for GCSE, GCSE, and as you remember before, we understand how to work with exponential equations and how to convert it into logarithmic form. So finally, to solve that for x. Today, our purpose is to get to know how to solve logarithmic equations for x, and basically it means that you need to use log by definition. All right, so grab your notes, grab your pens, and let's get started. Okay, so what we have log 3x equals 2. How do you resolve that? You just need to remember that by definition, log with the base a of a number b, or let's say of a number x, it equals to, let's say, another number b, so that if you raise a to the power b, you'll get x. So that's why this is the instruction for solution. So x is going to be a to the power b. So make sure you also remember that x is going to be more than 0 strictly, and that's enough to understand what your solution is and whether it works or not. So let's get started from the first one, log 3x equals 2, from where you can resolve for x. So just taking 3 raised to the power of 2, and that's solution for x. So 3 squared, which means that it's 9. As you understand, log x is more than 0, so that's why it works. Okay, let's go to the next one, log 3 of a number x minus 3, where the variable sits inside, equals to -1. What are you going to do? You need to do the same. So we're just taking x minus 3, and this is by definition equals to 3 to the power -1. So 3 to the power -1. But hold on, let's remember, if you have negative power, so how it works, it just simply flips your fraction or a number, so that you can write as 1 over 8 to the power of n. So that's why 3 to -1 is 1 over 3, so that's why finally x is 3 plus 1 over 3. That means you have x as 3 and a third. Or if you want, you can convert to a decimal. That means it's going to be 3 and 3 recurrent, okay? So periodical fraction. So whether it works, yeah, because if you plug x and check whether x minus 3 more than 0, it will definitely work, because 3.3 in the period is more than 3, so that's why the difference is greater than 0. Okay, let's go to the next one. We've got log 27 of x minus 1 equals to the fraction. We just do the same. We take 27 and raise to the power 2 over 3. So that's why I'll write as x minus 1 will be equal to 27 to the power 2 over 3. Okay, now to simplify that, we can write 27. So if we write 27 as 3 cubed, we'll get the following. So x minus 1 will be equal to 3 cubed and to the power 2 over 3. 2 over 3. So how it works, just remember indices law and indices properties. So just simply multiplying 3 by 2 over 3. That means 3 here on top and 3 in the bottom will be cancelled. So that's why it will leave you with x minus 1 equals 3 squared, which is 9. So finally we'll get x equals 10, and it's right time to check. So x minus 1 should be greater than 0. That means 10 minus 1 is 9, so that works, and this is solution. All right, and let's go to the last one here, log with the base x. However, that's weird, because we normally should expect to have x instead of a number, but right now we have x as the base. So we do the same stuff. We take an x and raise to the power 3. So that's how we can get 8. So that's why we can write 8 equals x cubed. From where we need to say that There are several ways you can take the cubic root of 8. That will stay for x. Or if you like, you can present your 8 as 2 cubed. So that means you align the powers, and because the power is the same, so should be the bases. So it means x is going to be 2. Or you can take the cubic root out of 8, so that means the same answer too. And let's check. So x also needs to be more than 0. So that's why you'll get x equals 2 as the solution. And let's go to and try how you can solve the word problem that's connected somehow to logs. So let's try to read. The population growth p in a town can be modeled by following equation. So p from time, so p is the function of time, equals p0 e to the power 0.035 t squared. So where p0 is 130,000 people and t is the time in years after the year 2008. So after what time will the population reach 250,000 people? Okay, so how it works? It works by plugging the initial amount of people, so the initial population, into the formula. And also you ask at what time will the population reach a given amount. So that means it's a p when t is the time that you want to find. So somewhere in the end. So actually first I illustrate how it works using graphs. So this is p, population, and this is timeline, horizontal axis. And let's draw the graph. For example, I can use that. Let's do it a bit bolder. Okay. So how it works? When t0, if you plug t0, so that's e exponent. So we know that exponent is simply e, which is around 271. Okay. So you can find easily on your calculator the button e to the power of x. So here is the button e to the power of x. It means that an exponent raised to the power of x, because exponent is the same as the pi number, it's irrational. However, my purpose is to demonstrate how the exponential function works and how it typically works here to show clearly how the graph looks like. It starts when t0, your p from 0 is simply, I just write p from time 0, t equals 0. It's your p0 because if you plug t equals 0 in the exponent, you'll get e to the power 0, which means simply e to the power 0 is 1, and you'll get p0. So that's why at some point of time, actually t equals 2000 and, the actual year, let's say the actual year is 2008, because that's the starting point, and t number of years from that time. So that means t equals 0, actual value for the variable t. And somewhere t years later, so you will have exponential growth. So exponential mostly, okay? So that's proportional to e to the power 0.035 and t squared. Okay, so that's how your function works. And somewhere when you have the level or the value for t, for time, somewhere here, you will see your value for p, okay? So that's how it works, and that's your p from time that you actually given. It's 250,000. So this is 250 and 1,000, and p0 is your initial amount of people, 130,000. Okay. So what we're gonna do, that's graphically I just show you for in case you want to understand how it can be modeled and what what the graph looks like. So right now what we're going to do, we just need to plug the values. Instead of function p from time, we're taking 250,000 here, and that will be equal to 130,000 times e to the power 0035 and t squared. So your variable t that you want to find is an exponent. So what you can do first, you can simplify it just simply by dividing 250 over 130. So that means you'll get 25 over 13. I just cancel zeros. And on the right side, you'll have this e to the same power. We didn't change the power yet. However, right now, what we're going to do, we're going to apply a ln, which means actually log with the base e, because we have e here and we want to get rid of that. So that's why we apply log e, or ln, that you might have the button on your calculator, ln. So ln is simply the button on your calculator. And what we will have, we'll have 25 over 13. From there, we take in ln. And on the right side, if we apply ln, we just simply get rid of ln, and we'll get 0035 t squared in the same manner as we did before. And right now, to get t value, we need to take what? The square root, right? So we're taking square root of, what we're going to do, we're taking the square root of ln 25 over 13, and we divide it by 0035. That's what we are going to calculate. So basically make rearrangements to make t as the subject. So that's our formula, rearrange, and that's how we can get the t value. And now grab your calculators. So use square root of the whole fraction, ln 25 13 and over 0035. So if you calculate that, actually I already did it, and I've got t is around 4.32 years. All right, so it means around 4, and third part means 4 months is around like 4 years. Yes, and around 4 months is because 0.3 of the year, it's simply 1/3. So that's why through this period the population will reach this value. So that is going to be a solution. So around 432. And this is how it works. Okay, hope you like that. Hope you understand everything. That was actually pretty. It seems to me that the last problem is pretty challenging. However, if you made this on exam, so you know what to do, guys. That was Daniel Dallas. We finalized logs equations and exponential equations, and it's right time to go to and start doing revision. This course is already there. See you later.